Alright, this problem is asking us to find a polynomial of degree 4 with real coefficients and the following zeros. So I like to start by breaking these into quadratics first. So there's a formula that you can kind of use to help you out with that, and using FOIL, you can see why it works. But x squared minus the sum of the roots plus the product will quickly turn this into a quadratic. So sum, this just means add the roots. Product, just multiply the roots. This minus sign is important. So let's deal with our imaginaries first. So we know if 1 minus 2i is a root, we know that 1 plus 2i is also a root, because that is, imaginaries always come in conjugal pairs. So the sum of 1 minus 2i and 1 plus 2i is just 2, because we add our real components. 1 plus 1 is 2. Negative 2i and positive 2i is 0. So then I have the first part of my quadratic, x squared minus 2x. And now I need to find the product. So I'm just going to use FOIL. So 1 times 1 is 1. 1 times 2i is positive 2i. Negative 2i times 1 is negative 2i. And negative 2i times positive 2i is negative 4i squared. Well, we know from a previous lesson that I squared is equivalent to negative 1. So a negative 1 times a negative 4 is a positive 4. Negative 2i, positive 2i goes to 0, and then we have a 1. So that product is just 5. So that gives me a second degree polynomial with roots of 1 minus 2i and 1 plus 2i, but we want a fourth degree. So now we need to pay attention to this piece over here. So we know that negative 1 has a multiplicity of 2. So if negative 1 is the root, we know that the factor is x plus 1. So now we need to evaluate x plus 1 squared. So I'm going to use FOIL to expand that. So x plus 1 times x plus 1. Lots of multiplication here. So that's going to give us x squared plus x times 1, which is x times 1 again, which is x, plus 1. So that gives us x squared plus 2x plus 1. So now we have it down to 2 quadratics. So if we multiply these, that's going to give us our fourth degree polynomial. Now, to make multiplication easier, you can always do, the box method, or you can use FOIL, whatever is easiest for you. With something this big, I like to use synthetic multiplication, which I don't think a lot of people know about, but I'm going to show you just because it's cool and so much easier. But I will do the box method real quick too, so just so you can see. Box method is it's just using the distributive property. Sorry, my pen has just a crazy lag today, and I don't know why. I've tried updates, but I will figure it out for the next one. Okay, so box method is just a nice, pretty way to organize multiplying polynomials. So x squared, negative 2x, 5, and then x squared, positive 2x, 1, and it doesn't matter which one goes on which. I can't even think of a word for that. Sorry, it's early. So x squared times x squared is x to the 4th. Negative 2x times x squared is negative 2x cubed. And 5 times x squared is 5x squared. Man, this pen's driving me crazy. And then 2x times x squared is 2x cubed. 2x times negative 2x is negative 4x squared. 2x times 5 is 10x. 1 times x squared is x squared. 1 times negative 2x is negative 2x. And 1 times 5 is 5. And now we just add like terms. So we have x to the 4th. And it's nice because the like terms are aligned in diagonals. So 2x cubed minus 2x cubed is 0, so I'm not going to write that in. Then I have an x squared, a negative 4x squared, and a 5x squared. So 5x squared minus 4x squared is 1x squared, plus another x squared is 2x squared. 10x times negative 2x is negative 20x, and then plus 5. So there's our polynomial of degree 4. But I do want to show you synthetic real quick for multiplying polynomials. So if you take just the lead coefficients, so 1, negative 2, 5, we just line them up, 1, 2, 1, always pulling in the signs. So think about normal multiplication, except you don't carry. So 1 times 5 is 5. 1 times negative 2 is negative 2. 1 times 1 is 1. Just like with normal multiplication, you leave a spaceholder here. 2 times 5, I don't carry, so I just write down a 10. 2 times negative 2, negative 4. 2 times 1, 2. And again, just like normal multiplication, now I leave 2 spaceholders. 1 times 5 is 5. 1 times negative 2 is negative 2. And 1 times 1 is 1. And then, just like normal multiplication, we're going to add everything. So 5, 8, 8. See, look, that's a nice way to check our work here. See what I did over here? I multiplied those for some reason. 10 minus 2 is 8. So that's always, see, I wasn't trying to show you how it's important to double check your answer, but that should be a positive 8x. 5 minus 4 is 1 plus 1 is 2. So that matches up. 0 and 1. I know that an x squared times an x squared is going to give me a quartic, 4th degree. So I know that now I just need to add my variables back in. So 1x to the 4th plus 0x cubed. Notice we don't have an x cubed. Plus 2x squared. And then there was my mistake. I say our, as if you were here. It's me. There was my mistake where I added 10 and negative 2 incorrectly. So plus 8x plus 5. So that, like I said, I think this is such a cleaner way to multiply polynomials. So this one is asking you to use something called the rational roots theorem to find all of the zeros. So there are 2 ways that you could go about this. The idea is that you do it all by hand, but you could actually extract a 0 by graphing it on something called Desmos, and then so you have a starting place to go through. But just to recap the rational roots theorem, it basically says that you have plus or minus p over q possible rational roots, this being p and this being q. So that means all of our possible rational roots. I'm going to start by adding out all of the multiples of p, so plus or minus 4, plus or minus 2, and then, as always, plus or minus 1. And now all of the multiples of 5, so plus or minus 5, and plus or minus 1. So then, to find all the possible rational roots, or zeros, you take plus or minus every possible combination of p over q. So that's plus or minus 4, over 1, so that's just plus or minus 4, and plus or minus 4 over 5. And then we have plus or minus 2 over 1, and plus or minus 2 over 5. And then we have plus or minus 1 over 1, and plus or minus 1 over 5. Now, really, it's pretty exciting that we can narrow down an infinite number of possibilities to just 1, 2, 3, 4, 5, 6, 7, 8, 10, 12, 14, 16, 18, 22 possibilities. So that's super exciting. What's not super exciting is having to guess and check your way through to figure out which one of these is an actual rational root. So to do that, again, the non-calculator version is just start by plugging them in. So we're going to use synthetic division. So I have a 5, a 1, I'm just taking the lead coefficients, a negative 20, and a negative 4. And what we are looking for is for this to go in perfectly, which means you would have a remainder of 0. So that's going to give us 5. 5 times 1 is 5. 6. 6 times 1 is 6. Negative 14. And we can already see that's not going to work, so then we move on and we try a different one. Okay, so now it's moments like this that I wish that I had looked at the answer ahead of time so that I could guide us to the right one to try. Let's try negative 1. Okay, so bring down a 5, negative 5, negative 4, positive 4, not looking good. Negative 16, so we can see that's not going to work, so let's move on to 2. I always go with 1 and 2 first, mostly because those are the easiest numbers to work with. Alright, so let's go with 2, see if that works for us. So lots of practice with synthetic division. Okay, 5, 10, 11, 22, 2. There we go. We got lucky. So we have a remainder of 0. So we know that 2 is a root. So 2 is one of our zeros. So there's 1. So from here, since we started as a cubic, we are now down to a quadratic. So 5x squared plus 11x plus 2. So at this point, you no longer have to continue using the rational roots theorem if you don't want to, because it's a quadratic and we know how to solve for the zeros of a quadratic. We can either factor, graphing is always an option, but again, the implied process of this problem is that we work through it without technology. So you could always use the quadratic formula at this point.